Alright, so here we are on 2.1, the tangent line problem. So we're going to talk about what the problem is with a tangent line, but first we've got to talk about what a tangent line is. If you remember from geometry, when you're talking about circles, a tangent line is a line that kisses off or glances off the circle right there at a single point. And you had a property in geometry that said that a radial line was perpendicular to a tangent line. Okay, so a tangent line touches a curve at a single point. If you were to extend a chord through a circle, now you have a line that intersects it at 2 points. That is called a secant line or a secant line. So touching 2 points, secant line, intersecting at 1 point is a tangent line. And we're going to talk about why the tangent line can be such a problem. And we're going to examine that through example 1. So what we have here is an enlarged graph of part of the function of 3x minus x squared. You can see that we have an x-intercept here at 0, an x-intercept at 3, and then because the property of parabolas with an axis of symmetry through their vertex, we know that the x-coordinate of the vertex is at the average of those two. It should be at 1.5. What I want to do is ask you how this graph is changing. Well, you would probably answer that by saying it's changing at a variable rate, because as we come in from the left, it seems like the y values are increasing, and then of course once we get past the vertex, the y values are decreasing. Now as we get up to the vertex, the y values are increasing at a decreasing rate. The graph is getting less steep, and as we go past the vertex, the graph is getting steeper again. So it's not only increasing and decreasing, it's doing it at a variable rate. So more specifically, if I asked you how was the graph changing at x equals 1, okay, let's draw this line straight up to 1, and it would intersect right about there. Well, you could tell me really nothing quantitatively. You could say qualitatively, it looks like the graph is increasing at that point. If you compared it to how the graph is increasing to the left, you might say it's increasing at a slower rate than any point to its left. And if you compared it to a point to the right, you could say it's increasing at a faster rate than any point to its right. But I am interested in talking about exactly how fast this graph is changing at that point, which ends up being the point 1, f of 1. So let's quickly determine what f of 1 is. F of 1 is going to be 3 minus 1, which is 2. Okay, so it does kind of come across here and intersect. Well, it turns out that talking about how that graph is changing at a single point is tantamount to talking about how or what actually the slope of this tangent line is, which I'll move down right there. If I can find the slope of that tangent line to the curve at the point 1, 2, or point 1 f of 1, I will know exactly quantitatively how fast that graph is changing at that exact moment. Okay, well, what's the problem with that? Well, the problem with that is in algebra 1, we know that the slope is the change in y over the change in x. So delta y over delta x, or x sub y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Which means to find the slope of a line, we need at least 2 points. Well, therein lies the problem, because we only have 1 point on the line. And if I were to choose another point, say this one, I would be guessing. And we want to be a lot more accurate than just guessing. So there's the problem. How can we figure out the slope of a tangent line to a curve at a single point when the current mathematics of the day requires 2 points? Well, the answer is simple if you're a genius like Leibniz and Newton. You're sitting around in the 17th century without any distractions like Facebook, social media, Xbox, or whatever it is that occupies your time nowadays. You simply invent a new branch of mathematics called calculus. Although back in the day, it wasn't called calculus. Leibniz, the German, called his the method of infinitesimals, and Newton called his the method of fluxions. Okay, now we're going to kind of derive how that came into being using the much later technology or notation, the idea of the limit. Because neither Leibniz nor Newton used the idea of the limit. Leibniz came really close talking about his infinitesimal, which is infinitesimally small. Newton essentially divided by 0, and wow, that's pretty cool. We'll show that in a later episode. So to do that, let's say that we have to use the calculus of the day, which means that I have to use another point. Okay, so let's say that I choose another point. Let's say I use the points, and I'm going to come down here to example A. I'm interested in the point 1 f of 1. That's really what my target is. But I'm going to choose another point that the algebra of the day is requiring me to use, and I'm going to choose it to be the point 1.5, f of 1.5. Okay, now I can plot that point right about here. Let's just say it's right there. That's where the vertex should be. If I were to draw a line connecting those two dots, it would look something like that. And there you would go, make your dot bigger if you missed the line. That would be the secant line. And now that I have 2 points, I can find the slope of that secant line. All right, well, I have set up the average rate of change between those 2 points, which will, in essence, give us the slope of the secant line. And that's kind of the first big connection, because Newton was all about motion and the application. And so he was interested in finding the slope of the tangent line as an instantaneous rate of change. Leibniz was interested in finding the slope of the tangent line. But the algebraic versions of those, instead of finding an instantaneous rate of change, the Newtonian perspective would be to find the average rate of change. And instead of the slope of the tangent line, the Leibnizian perspective would be to find the slope of the secant line. And it's interesting because they both invented calculus, Newton and Leibniz did, at roughly the same time, but at completely different parts of the world, using completely different notations, and they were motivated by very different things. So I'll keep talking about the Newtonian perspective, which is motion, instantaneous and average rate of change, and the slope of the tangent line and secant line, the Leibnizian perspective. Okay, so we are going to set up the this right here. This is called the difference quotient. And this is exactly what you did in Algebra 1 when you were finding the slope of a line. It's delta y over delta x, but I'm using f of the change in f over the change in x. Okay, so now instead of doing this by hand, here's what I'm going to do. I've already got my equation typed into y1. This is using a calculator in a smart way. So I've got 3x minus x squared. Now from my home screen, I'm going to recall my horizontal division bar. So that's alpha y equals, and then select number 1, and I'm going to type in f of 1.5, but my function is in y1. So you can get there 2 ways. You can hit bars, click to the right to the y variables, enter function, and there's all your y's. My function's in y1, so I'll select it, and if I open the parentheses, type in 1.5 and close it, now all of a sudden I have essentially the calculator will compute that as y1 of 1.5. So then I just go minus f of 1. Well, if you have the new math print operating system, it's pretty nice. You can hit alpha trace, and you can get it that way as well. It's a shortcut. But again, I'll just put of 1. And in the bottom, I know 1.5 minus 1 is 0.5. I'm going to go ahead and type it in. Now if I hit enter, I get 0.5. So that's going to equal 1/2, or 0.5. So what that means is that the slope of this secant line is equal to 1/2. Now that could become an approximation for the slope of the green line, the tangent line, which we really want, right? People who are content with mediocrity, they might say, yeah, that's close enough to me, for me, but people that are content with mediocrity don't really advance the world forward. So what we'll end up doing is we'll choose a point that's a little bit closer, and if you look at part B, I already have the ratio, the difference quotient set up, but I'm using the points now 1f of 1, which is 0.12, that's what I'm interested in. And now I'm choosing a point that's a little bit closer. We're going to 1.1 now instead of 1.5. So now we are a tenth away from the 0.1 instead of a half unit away. Now to calculate that difference quotient, or the average rate of change between those 2 points, or the slope of the secant line, I'm just going to recall, second enter, my line from above, and I'm going to scroll back, and wherever there's a 0.5, I'm going to change it to a 0.1. And all we have to do is hit enter again, and we get 0.9. So maybe I should have kept that as a decimal. This we can compare decimals. We want to call it 9/10. So how about 0.5? Now we got 0.9. Okay, so then we can now say, and I didn't draw that up here. Let me see if I can draw it in purple. The point in green is what we want, so 1.1 might be right around here, and it's on the curve, so if I draw this line here, it might look like that. We just found that that slope is 0.9. So now the purple slope is a better approximation for the green slope, the tangent line slope that we actually want. But I think we can do better than that. So let's choose a point that's even closer again. So now again, the points I'm using are 1 f of 1, the point I'm interested in, and the other point I'm going to use is only now 1/100th away, 1.01, and then its function value as well. So the difference quotient is set up above, change in the f values over the change in the x values, corresponding x values. So once again, I'll recall it. I'll hit enter, second enter, and I go back now, and I want to insert a 0, so I'll hit second delete, type in a 0, scroll up, come back here, type over the 1, second delete is insert, insert a 0, and hit enter, and I get 0.99. Okay, now it's going to be increasingly hard for me to draw, let's do a pink, to draw these lines that are going to use 2 points that are closer and closer together. But you can kind of see, let me extend that one out, you can kind of see what's happening here is that as I move that second required point closer and closer and closer to the point I want, I'm not only getting a secant line slope that becomes a better and better approximation of the tangent line slope, I'm actually getting the secant line slopes to slowly converge towards what will become the tangent line slope. So I'm not going to draw this next one, but here I'm using the 2 points. We'll just keep it in pink here. 1 f of 1 and 1.001 f of 1.001. So this is 1,000th of a unit away. And if you're thinking about time on the x-axis like Newton did, this is letting only 1,000th of what might be a second pass by before you take the 2 readings of something's position to determine its average velocity over that very, very tiny time span. So let's just do one more time here. Scroll back, and I will add one more 0. And then go to the top here, scroll back, and add one more 0. Second delete 0, enter, and you get 0.999. Now here's the beauty of this process. I can continue choosing that second point closer and closer and closer and closer and closer to x equals 1 simply by adding more and more zeros right there. And I can do it indefinitely. Now I have the benefit of the calculator to make the computations for me, and back in the old days they sure did it. PC before calculator, they didn't have it. But I don't think I need to compute that anymore because I think I can already see the limiting process here. The limiting process is taking the limit as that second point gets closer and closer to the first point. And I can already see that maybe the slopes of my secant lines are approaching some limiting value. 0.5, 0.9, 0.99, 0.999. Maybe the next one will be 0.999, and then eventually 0.9999999999999, which is really, really, really close to 1. So part E here, based upon the mathematical evidence above, how fast is the graph of f of x changing, not between 2 very brief moments in time, but at the single moment in time at x equals 1? Well, it would appear that its slope, that is the slope of the tangent line, is 1. Okay, that's what this evidence tells us, that all of this is approaching 1. So if I come back up here, I can now answer my own original question. If I look at the green line here, which I'll highlight for you because I know I've kind of done a lot there, this green line is the tangent line. So now if I ask you one more time, how fast is this graph changing at x equals 1 or at the point 1, 2, you can now say that it is increasing 1 unit vertically for every 1 unit it's going to the right, or the slope of the tangent line is 1. So there you go. That is the instantaneous rate of change as well as the slope of the tangent line. It's instantaneous, and it's only good for that instant because in the very next instant the slope of the tangent line is going to be a smaller number, and immediately before that the slope of the tangent line is going to be a bigger number. But at that instant, that graph is going up 1 for every one it's going to the right. That's pretty darn cool. So here's the next evolution of the calculus. So I chose 2 specific points, and I looked at that second point getting closer and closer and closer to the one I wanted. Well, the next evolution is to be just slightly more clever. I'm still interested in the slope of the same graph at the point 1 f of 1. But now I am going to define the second point that I have to use to be h units away from that original x value. You can think of h as being just some very small hair's width away. Now let me show you what that's going to entail. So if I choose my second point, and I'll choose, let's choose orange here. I'm just going to choose an arbitrary point. I'm going to get rid of this. Don't need it anymore. Alright, so I'm just going to draw an arbitrary line up from somewhere near 1. And I'm just going to draw it to the right of 1, although it would work to the left of 1 if I wanted to, until I come up and hit the parabola. The parabola I have the equation for, so I can generate as many ordered pairs as I want, just by choosing as many x values as I want. Now, instead of calling that point like 1.1 or 1.2, I'm going to define this distance between the point I want at x equals 1 and the point I have to use. I'm going to call that h. So that this point becomes 1 plus h. I can define it in terms of the point I want. Now, h is just a fancy single letter for a delta x, a measurable width delta x. I'm just going to use h because it's a single variable. So the y value up here should be f of 1 plus h. Alright, so now with those 2 points in hand, I can come up with the same thing I did before. I can find the average rate of change between those 2 points, and I'm going to set it up right now. So it's going to be the change in the y value over the change in the x value, which is going to be f of 1 plus h minus f of 1. That's the change in those 2 y values over 1 plus h minus 1, the change in the corresponding x values. Now I'm going to clean that up just a little bit because it does clean up. I get f of 1 plus h minus f of 1. In the denominator, 1 minus 1 becomes 0, and I'm just left with h. And again, that's to be expected because I am finding delta y over delta x, and I told you already that h is just a fancy single letter version of delta x. Now what this becomes, this becomes a formula or a function for a, what I'm going to call a, the average rate of change function. Okay, but it's going to be as a function of h, the distance between the 2 points. Okay, so let's go ahead and set it up. I can actually evaluate, oops, did that wrong while I was talking. I'm actually going to evaluate f of 1 plus h. Remember our function is 3x minus x squared. So I'm going to plug in a 1 plus h up here for every x that I have, and this becomes 3 times 1 plus h minus 1 plus h squared. And maybe I'll highlight it so you can see that this is this right here. Now in, let's use gray, this is f of 1, and I can go ahead and just subtract what I know f of 1 is, or if I want, I can use parentheses and say 3 times 1 minus 1 squared, and of course I will get 2 like I did before. But I did this so that you would realize that because there's a minus sign there, you would need parentheses if you didn't know what it was. And it's all over h. Now we can simplify this, so I'm going to go ahead and simplify it. The average rate of change function as a function of h, the width between the 2 x values, becomes 3 plus 3h minus, I'm going to go ahead and square multiply double square and distribute the negative as I go. So that's going to be minus 1. If you multiply w, you get 2h. Distributing, you get minus 2h. Square the last, you get h squared. Distribute the negative, you get minus h squared. And then, of course, that becomes minus 2 all over h. Well, we can simplify that even more. The average rate of change function is a function of h. If we look what's going on up there, I'm going to have a 3 minus 1 is a 2 minus 2 is 0. And that leaves me with 3h minus 2h, which is h minus h squared all over h. Now, notice that if I let h equal 0, okay, if I come back up here and I let h equal 0, then I really don't even have 2 points anymore. I have the same point, 1 and 1 plus 0, which is 1. And I'm back to the same problem of having only 1 point and needing 2. Okay, and you can see that right now if you try to evaluate this when h is 0, you're going to get 0 over 0, which is an indeterminate point. But here's kind of where the magic starts. We can factor that h out, and we're left with 1 minus h over h, and if I divide those h's out, I'm going to come back over here, I get this new simplified version, which becomes nothing more than 1 minus h. 1 minus h. Of course, I might warn people that we're not going to let h equal 0 because, again, I've removed the denominator that kept it from happening, and I know that if h is 0, I'm back to using 1 point. Now, this would be pretty handy for anyone that was interested in doing these tedious calculations up here that I did on example 1 without a calculator. The calculator really did all the heavy lifting. I didn't want to have to go 1.01 times 3 minus 1.01 squared. The calculator did it for me. So not having a calculator, I can be very smart now and use this formula, the A of H formula, to do all my calculations for me. And let me show you what I mean. If we return to 1A, remember the 2 points that we used were the points 1f of 1 and the points 1.5, f of 1.5. So in this problem right here, since the point I was using besides x equals 1 was x equals 1.5, 1.5 is a half unit away from 1, so that would mean h is equal to 0.5, or 1/2. I'll use 0.5. So to find the average rate of change between those 2 points, all I have to do is say a of 0.5, then it becomes 1 minus 0.5, which is 0.5. And I get the answer without any real tedious calculations. So that's pretty darn clever. Let's do one more. Verify 1b, not 1a again, 1b. The points were, of course, 1f of 1, the point I'm interested in, and that was 1.1 f of 1.1. Well, rather than compute the difference quotient with those tedious numbers, 1.1 is a tenth of a way from 1. So if I let h equal 0.01, I can calculate the average rate of change with an h value of 0.1, and I get 1 minus 0.1, which is, of course, 0.9. That's pretty sweet. Okay, so now we are now ready to answer part B. What happens to the secant line between the points 1, f of 1, and 1 plus h, f of 1 plus h, as h gets smaller and smaller? Well, notice as h gets smaller and smaller, as we saw up above, let's just use another one, 0.11, or 0.01, sorry. That's going to be 1 minus 0.01, which is going to be 0.99. So you can see the same thing happening here numerically as what we did up above with the calculator's difference quotient numbers. But here is again where we're kind of taking our clever leap with the limit. If I take the limit as h approaches 0 of my function a of h, that would be the same as the limit as h goes to 0 of 1 minus h. I know when I say the limit as h goes to 0 that I'm not really letting h equal 0. We've already studied the limit, so we know that just means that you're getting closer and closer and letting it happen. But we also know that we can evaluate it now because we've gotten rid of over here the 0 over 0 problem. We can evaluate it by direct substitution. So here we go. Plug in a 0 for h and we get 1 minus 0, which is 1. And that was a calculus move. That was a huge step right there, introducing the limit. So what we can say then is the limit as h goes to 0 of a of h is 1. And now, without using the calculator, we have essentially computed that the tangent slope of f of x at x equals 1 is 1. The instantaneous rate of change of the function f of x at 0.12 is 1. At that exact moment, it's going up 1 for everyone it's going over. So that was a pretty nice evolution, right? Using a second point as a function of h, so we can force h to approach 0. Okay. Well, that's fine and dandy and all, but now let's say I wanted to find the slope somewhere else. Okay, like maybe over here past the vertex. Let's call that, I don't know, 2.4, 2.3. I know it's negative from the graph, but if I wanted to figure out quantitatively what it is, I would have to set this entire ratio up again. And I don't want to have to do that. So here's the next evolution, example 3. If I let the point 1f of 1 just become the general arbitrary point x f of x, pretending the whole time that x f of x is a constant, much like 1 f of 1 was a constant, I can do the same trick I just did, choosing my other point to be h units away. So my other point will become h plus x, or x plus h, f of x plus h. Let's see what that would look like. I'm going to try and fool the math. I can say now that f of x plus h minus f of x all over x plus h minus x is going to give me the same thing I had above. Now I'm going to try and fool the math into thinking that x, f of x are constants, and h is still my variable. Well, if I simplify that, I get this all over h. And I'm going to do one other thing here. Instead of taking the limit at the very end, like I did over here, after I evaluated it, which works fine, I'm going to go ahead and just throw it in there in the beginning, knowing that I will take the limit of it, though, at the end. But I'm going to have it there the whole time. So here we go. Let's set it up, and then we evaluate it. F of x plus h is going to be 3 times x plus h minus x plus h squared, because f of x is 3x minus x squared. So there's the first one. I'll highlight it so you know what I'm doing. There's that one. And the next one would be minus f of x. So that's going to be minus 3x minus x squared. Now notice I do need the parentheses there, unless I want to distribute, and I don't want to do too much in one line. So there we go. We've set it up. Now if I simplify it again, keeping my limit out front, and oops, that should be the limit as h goes to 0. I should speak up at home if you see that. Okay, so now I'm going to distribute 3x plus 3h. And again, square multiply double square and distribute the negative. I get negative x squared minus 2xh minus h squared. And distributing here, I get minus 3x plus x squared all over h. And if I set it up right and expand it right, again, good things should happen. Minus 3x plus 3x minus x squared plus x squared. And everything that is left in the top has an h in it. So if I were to plug in an h right now, I would still get 0 over 0, which I perfectly understand because that would still be using one point, and that's the tangent line problem. But what I can do now to circumvent the 0 over 0 is I can factor out the h that's there and get this all over h. And then, of course, now we know how to evaluate the limits. Divide out the h over h, and anything that's left I will plug in a 0 for h. And so there's only one. I have one here and I have one there. So if I plug in, I get 3 minus 2x minus 0. Now, this is totally awesome because I was pretending that h was a constant all the way through and h was the variable, and it was for my limit. But now that I've come out with this formula, I can actually let x float again as a variable. And what I have now is a little expression that will give me the slope of the tangent line to this graph up here, right there, at any value of x that I choose, any one of them. Now this is the breakthrough, because this is what we are going to call f prime of x. And we write it as f with a little hyphen of x. Again, we read that as f prime of x, and it becomes the derivative function. That is what name we're going to give that. We're going to call f prime of x the derivative function. So notice the function we're talking about, whose y values we're looking at, is f. F prime now is related to f, and that's why we use the same name. But it's not the y value function, it's the derivative function. You can also call it the slope at a point function, or the slope of the tangent line function. You could also call it the instantaneous rate of change, ROC function. They're all the same thing. This is Newton and Leibniz. Leibniz was the slope at a point function. Newton was the instantaneous rate of change function. We're going to call it the derivative. So now let's verify. Let's see. If I want to figure out what is the slope of the tangent line or the instantaneous rate of change at 1, I don't have to reinvent anything. I'm just going to use my handy dandy f prime of x equals 3 minus 2x. And if I want the slope at 1, I'm going to plug it in, get 3 minus 2 times 1, which is 3 minus 2, which is 1. What we just did right there, that was something Galileo worked his whole life to try and get. An explicit formula into which he could plug a single value of time, x, essentially, to get the instantaneous velocity of an object. And all he was able to do was what we did way up here. But pioneer for his time. Okay? So, yeah, we take that for granted. Now let's go ahead and do that other one. What if I wanted to figure out what f prime of 2.5 is? Okay, where is 2.5? Well, it could have been right here. Somewhere right in there. I know it's going to be a negative number. I don't have to do anything anymore, setting up the limit, setting up the difference quotient. I just drop it into my handy dandy derivative function, and I get 3 minus 2 times 2.5 is 5. I get negative 2. So at that point, the function is decreasing 2 units for every one it's moving to the right at that point. That's its instantaneous velocity, rate of change, or its instantaneous velocity. Newton would say that the y values are decreasing by 2 feet per second, let's say. Decreasing because it's negative. Now here's what else is cool. You can use this new thing as a formula, which means if you know an x, plug it in and find the slope there like we've been doing, or the other way around. If you know what you want the slope of the tangent line or the instantaneous rate of change to be, you can set it equal to 0 and solve for x. So here's what I want to do. I want to find out where the vertex is. I want to find out where the vertex is. So the vertex is up here again, and I know it's already at 1.5. But if I were to draw the tangent line at the vertex, it would be a very special tangent line. It's a horizontal tangent line, and a horizontal line has a slope of 0. So let's verify that it's at 1.5. If I took my derivative function, f prime of x, and I set it equal to 0, the slope I want it to be, that's the same as 3 minus 2x equaling 0. I can now solve for x. 3 equals 2x, x equals 3 halves, or 1.5. I just verified using my new calculus derivative, slope at a point function, instantaneous rate of change function, that the x-coordinate of the vertex is at 1.5, where I already knew it was. Now you don't need any special calculus tools to find the x-coordinate of the vertex of a parabola. Because if it's not, if you don't want to use the average of the x-intercepts, you can always put your parabola in standard form, ax squared plus bx plus c, and then use the first part of the quadratic formula to find the x-coordinate. That works as well. But here's the power of the calculus. This is another motivation for inventing it besides the tangent line problem. Let's say that we have a business, we're running a business, and we are talking about dollar signs, cha-ching, up there in terms of our profit per X units that we make or sell. We want to run at an optimal efficiency. We want to be very efficient. We want an optimal level so that we can maximize our profits. Well, there is no necessary way to find these local extrema. This would be a local max, local min, local max, local min. This would be a local max and an absolute max, local min, local max. But if I can find an equation for that model, which is not very difficult to do now with computer programs, curve fitting, we can actually take the derivative of this, let's call it p for profit function, as a function of x. If I take the derivative of that, which we're going to be able to do, and set it equal to 0, I'm going to be able to find all of these different x values, x of 1, x of 2, x of 3, x of 4, and now I can perform at the optimal level to maximize my profits. So the max-min problems were also a motivation for calculus in addition to the tangent line problem. So let's summarize here, and then we'll see what else we can do. This box summarizes what we just did. Now I'm going to read this to you. It says the slope function found in the previous example is called the derivative function. I told you that, of f of x, and we call it f prime of x. It can be used to find the slope of the tangent line to a graph at a point, so just slope at a point, or also the instantaneous rate of change. Now here's the definition. A function that has a derivative at a point is said to be differentiable at a point, or at that point. So there's a new vocabulary word, differentiable. If a function is differentiable at a point, then the derivative or the slope of the tangent line exists at that point. Now, we can talk about the formal limit definition of the derivative of a function. If f is differentiable, that means if it has a derivative, then its derivative function f prime is said to be this. F prime of x is equal to, the limit as h goes to 0, of our difference quotient between our 2 points, x plus h, f of x plus h, and x f of x. So there it is. If we let h go to 0, we are forcing those 2 points to converge to each other. And so what that means is the slope of the secant line converges towards the slope of the tangent line. Alright? Now with the limit there, we don't have to sneak up on it anymore. We can actually compute it analytically because we know how to evaluate the limit. So this is definitely something that you're going to want to memorize for sure, for sure, for sure. Now before we jump into example 4, we're going to be using other notations for f prime of x. If we're starting with an equation y equals instead of f of x equals, we can use y prime. That's what we call it. But I like this one. This is something that we can read informally as dy dx, but it's really spoken as the differential of y with respect to the differential of x, or the derivative of y with respect to x, either way. This is Leibniz notation. Leibniz didn't get credit for discovering the calculus in his own time, more or less. He had a few supporters, some Bernoullis, but they squabbled with each other. So he never got the fame, and of course not the fortune that maybe he could have and should have deserved, because Newton was kind of the head of the Royal Society and kind of made sure that Leibniz was a footnote in history. But anyway, we don't use Newton's notation. Newton's method of fluxions used some weird symbols with some dots, and he also divided by 0. So even though Leibniz didn't get credit, today we still use his notation. This is a carryover from Leibniz notation. dy is called the differential of y, and dx is called the differential of x. Now what is the differential of y and what is the differential of x? Well, one of the nice things about Leibniz notation is that it does kind of model analogously to what the slope between 2 points is, right? We call it delta y over delta x. Leibniz called his derivative dy dx. So one nice thing about Leibniz notation is it preserves that slopey feel to it. It has a change in y over a change in x. It also is nice because it defines your dependent variable. Y is your dependent variable, and x is your independent variable. So you can see how the dependent variable changes with respect to your independent variable. So that's another nice thing about Leibniz notation. Now here is what the differential of y is, to answer my original question. Delta y is a finite measurable change in y. It's a finite measurable distance. Leibniz called the differential of y an infinitely small, comma, immeasurable change in y. And very similarly, the differential of x is an infinitely small, immeasurable change in x. Now, I don't know if you know your vocabulary words, but something that is infinitely small, we say is infinitesimally, there you go, small. And that's why Leibniz called his method the method of infinitesimals. He called those the ghosts of departed quantities. Poof. It all spoke so much more poetically back then. So anyway, there is no way to measure dy or dx because it is infinitely small. So Leibniz didn't use the limit notation, but the limit idea is kind of contained inside the differential of y and the differential of x, because it's getting closer and closer and closer to 0, infinitely small, that you can't measure it. So it's another benefit of using Leibniz notation. Alright, I'll catch you on example 4. We're going to do that one here in a little bit.